Today's session is simply a summary of. Are you able to see the screen?
Yes, sir.
Okay. So, we will discuss on simply the summary of what we learned so far. Summary of what we learned so far. So far only in this columns and struts, because we have completed it. Columns and struts. What we have discussed, that's what I mean, what is a summary, so that you will not lose out of the track. So, the first thing what we did is that we understood the column fails by two ways. One, by yielding, right. We also another term is called, we can say, crushing. So, column may yield or crush. Another way is that column may buckle. Okay. Column may also buckle. Okay. Buckling will take place. So, this is early buckling. Okay. Buckling is earlier than yielding. So, this we said F y, or we said F c, crushing strength or yielding strength. So, the buckling we said somewhere like sigma e, yielding strength. Okay. So, this is what we said. So, when it comes to the crushing, and generally it is load coming, which is crushing load divided by cross section area. Okay. This is what we know, that column crushed, we continue applying load P till this column get yielding, or also called a crushing. Okay. But comes to buckling, a phenomena which is unstable phenomena. That means, if a column something like this, when you continue applying load at this one particular point, suddenly you see there is a lateral deformation will take place, right. So, that phenomena we call it as buckling, although load is axial. So, what is the difference between buckling and bending? So, buckling is the axial load, deformation is lateral side. Bending is the load lateral side, deformation also lateral side, right. So, this is the difference between buckling and bending. Okay. So, now when the load will not, I mean the load will not cause yielding or crushing, but the load may cause buckling. So, then what is the capacity of the column just before it is going to buckle? I am stressing the word just before. So, once buckle, it is going to collapse only, it is going to be too high. Okay. It is going to increase and increase, because this y is going to increase, load is same, y increase, further capacity decreases, y increases, further capacity decreases till it collapses. Okay. So, this is what you have to observe as far as the buckling is concerned, is collapse. Okay. Now, so what is the capacity of a column when it is going to buckle? So, Euler's theory is that he found out that if suppose I have a E is a buckling load, okay. This is, I mean, he has proved it, that we already did it, pi square E I by your L square. He said your load capacity just before buckling is proportional to your moment of inertia and your material constant, which is Young's modulus, and inversely proportional to your effective length. I say effective length. So, he has proved it. Okay. So, this is very important. So, that means E is your Young's modulus, right. E is your Young's modulus of velocity, right, modulus of velocity, and I is the important, which is I am saying least moment of inertia, very important, not just moment of inertia, least moment of inertia, whichever direction the column going to buckle. Okay. Column has possibility to buckle any direction. So, whichever direction is the least moment of inertia, that moment of inertia you have to use it here. L effective is effective length, right, that this is effective length, and we said it depends upon the end conditions. Okay. So, it depends upon your end conditions. So, we have studied different end conditions. The end conditions are, we started with end conditions. So, we could use only this formula with a change of L. So, if there is a hinge to hinge, so one end hinge and next end also hinge. So, what we say that one end hinge, other end hinge, that means my column something like this, hinge, right. So, let us this also I leave hinge. So, when apply load here with a P load, so column going to, so then entire length of column is going to buckle. This is we say L. So, in that case your L effective will be your L. Total length of column is effective length. Now, if my column is, let us say, a hinge and fixed and hinge, then what is L effective? So, we said this is a hinge, and the other condition is a fixed hinge. That means, let us say the column is fixed here, other side is your hinge, right. You are applying a load P. So, what happens, since it is fixed, if you look at carefully, the buckling behavior shows something like this. So, for distance it will not buckle. So, this length we call it as L effective. Okay, L effective, whichever amount of the length of the column which is buckling, the portion of column which is buckling, this is your L by root 2 we said. Okay. So, we also call it as 0.7 times L. L by root 2 is also called 0.7 times L. Okay. This is also L by root 2. Okay. So, next column which is your let us say fixed, right, and you say fixed. So, in the fixed column, the effective length will be, so very clearly again I am giving you here, this is a column fixed, this is a fixed. So, the deformation can be seen only at some distance like this. So, the length which is buckled is your L effective, which is nothing but your L by 2. Half of the length only got buckled, which is equal to L by 2. The next one is your fixed free column. So, for that L effective will be, so I have a column which is fixed here. So, I am just applying load P which is free here. This example of a water tank on the top, right. So, what happens? It is going to buckle so freely, it is something like this. So, what we do? So, the entire thing is buckling, if it gets free, this is your total length and it is assumed to be other side, this is also L. So, total length is your 2L. So, this is what we can see. So, that based on this understanding, load capacity of the column, if I just try to categorize the capacity of the column for the same length, same material and same geometry. If you keep all three parameters same, right, then the first highest load carrying capacity is for this fixed. Next is your this, next is your this, and the least is your this. Okay. So, this is how we can categorize the load carrying capacity of the column based upon end conditions. So, we said this. Then after that we also said something new, that this, although Euler gave me the formula, right, Euler gave me the formula, but it has got of course limitation. Anyway, before that we want to say that P e equal to pi square E I by L square, although L is effective. So, I can also write this I is another format, which is radius of gyration E into we know that I moment of inertia is equal to A into R square, A into R square by L square, and then we said pi square E, A got this side, P by A, which is we say sigma E, is by L by R. L is L effective, R is radius of gyration, that to least radius of gyration. So, this term L by R we termed as slenderness ratio, and where R is nothing but your radius of gyration. Radius of gyration is what we discussed, right. So, this is very important term. Sometimes your column, the slenderness ratio will be given to you. So, if you have to find out the buckling capacity, buckling strength is this, if slenderness ratio is given to you. Okay. Any dimension property of related to radius of gyration or slenderness ratio, you have to use this formula. So, then we went on finding the limitation of this theory, because he has not counted one important point, is that, so if you try to plot this lambda versus your stress, you plot lambda versus stress like this, and lambda in x axis, this is also called a lambda, L by R, L by R, and this side is your stress, and what we see, the curve goes something like this, and that is all, it is going to break. So, this point will be my lambda minimum, right. Less than that, my column is going to yield, right. So, that means this formula does not work. Lambda, let us say lambda is equal to, let us say 89. So, lambda anything less than 89 for a steel of Fy equal to 250 Newton per millimeter square, this formula will not work. That means beyond means lesser than this lambda, the column going to yield, right. So, this is called yielding zone, and remaining zone is called buckling zone. So, Euler's formula is not universal, it has got limitation, right. So, this lambda 89 is for steel. So, some other material, something else, right, that you can work out based upon your this pi square E. Okay. So, if you, and then this side is your yield strength, pi square, and E is there, and lambda the sigma yield, assuming let us say this you going to yield. So, you have yield stress, you have Young's modulus. So, you can work out what is the minimum, the lambda on which this Euler works. Okay. This is what we said, and then we said that apart from this, the Euler has derived this formula based on so many assumptions, right. We said he has made assumptions, very important assumptions, and if you look at the assumptions, so many things are there which this formula does not work in that area. One, the column is straight, he said column must be straight, which generally column is not straight, and say loading must be concentric. The general leak loading is not concentric, right, and even the material is uniform, right. Material is uniform, that means isotropic, uniform, and also cross section area also uniform, cross section area also uniform, right. So, cross section area throughout the length uniform, and so on, so many things we discuss, right. So, although there are ideal conditions, these are only ideal conditions on which your formula, your this assumption works, but practically most of this things is not true, right. So, hardly one or two may be right what he said, but other things are not going to valid. Okay. So, one by one, taking his limitations, taking the limitation of your Euler, taking the limitation of Euler, the Rankine came up. Rankine Gordon, he came with a formula which is empirical formula. Empirical formula means which do not have proper derivation, but it based upon your experimental results. So, he is concluded. Okay. So, then he said this particular formula is nothing but 1 by P. If P is your actual load carrying capacity, is equal to 1 by PC plus 1 by and PE. So, PC is your crushing load, and PE is your Euler load, Euler buckling load. Okay. So, Euler buckling load. So, according to that, so if you look at terms like this, the P was equal to sigma C into A by 1 plus alpha times your L by R whole square. So, we know that sigma C into A is nothing but your PC crushing strength, this is crushing load. Okay. So, this alpha is a constant, we understood. This alpha is a constant depends upon your material. Okay. That we can work out. So, that alpha is nothing but is my sigma C by pi square E. So, for a given material, sigma C is constant, pi square E is a constant. So, that is alpha. So, that means the Rankine takes care of sigma C crushing as well as L by R means your Euler, slenderness ratio means your Euler, right. So, Euler also taking into account Euler's and also crushing. So, he is taken care of the one of the important limitation this Euler has given. So, practically for your problems solving, so what is given to you as a part of the problems. So, you alpha will be given to you, just like alpha equal to 1 by 7500 for steel, file steel. Okay. Sigma C will be given to you. So, you can work out load carrying capacity based upon your area and slenderness ratio L by R. This is a standard problems, but he will mention specifically that you have to use Rankine Gordon formula or simply Rankine formula. Okay. So, this is your one. So, then comes to your what if another limitation that Euler has got, the load is acting, right, load is concentric. He said load must be concentric, load is concentric. That means, if I take a cross section something like this, right, this is one of the axis, is another axis, and this is a CG, center of gravity. So, this must be the position of P load, right, very ideal, just like and the parents, right. So, ideal condition that students, my son will go to the college exactly and to the class, listen a class, come back, right, that is a very ideal condition. So, load is concentric, which is practically not true. Then, so what happens if there is load is eccentric? So, what happens is very important. It is also important because this is practical things which Euler is very ideal condition, ideal man. What happens with eccentric loading? So, there are two ways to address this eccentric loading. One, you can find out the stress corresponding to the eccentric loading, which is load by area, which is assuming that transferring the load. Suppose the load is somewhere here, the P. So, P by A anyway actual load plus, and this load is going to cause a movement which is equal to m equal to P into E because of eccentricity. So, m by z section modulus in the direction of the buckling. So, one side is a plus, other side is minus. So, if it's buckling like this or eccentrically this side, so compression P by A plus m by z, the opposite side, that means this side, so this side is minus and stress in this side is a plus, I have to consider. Okay. So, this is your stress. Second thing is, I have to find out what is what is the area minimum required, so that tension will not be there in the column. Okay. So, total area I have to work out such a way that, I mean load distance I have to such a way that there is no eccentricity. Another thing is, there, I mean even if eccentricity is there, there is no tension in the column. Or another way to say that what is the maximum P, so that eccentricity is within the column, right. So, P max. Okay. So, to take care of this, we have a secant formula. Again, there is a derivation, you need to remember the derivations. You may be asked to derive the equations in the examination. This is called secant formula. Again, I will derive in the class based upon your end conditions and taking a column, fixed column, something like this, right. The load is here, which is already distance of buckle, and sorry, load is here with eccentricity E. So, this is not a load. So, load is here, column buckle, distance of A, and eccentricity is E. So, A plus E is the total movement, P into A plus E is the total maximum movement here, right. The P into A plus E is the maximum movement here. So, based upon your, let us say this is your Y. So, taking that movement equation and then using boundary conditions, so we derived the equation. So, the secant formula says that the maximum movement m max maximum movement in the column is equal to P into E into secant of L by 2 into root over P by E I, right, and maximum stress sigma max is equal to P by A of 1 plus E into YC extreme fiber distance by R square radius of gyration into secant of L by 2 root over P by EI. Okay. So, this is maximum stress. Remember the terms here, that L is your effective, right. L means L effective, which is again based upon your the end condition L or L by root 2 or L by 2 or 2L according to the end conditions. Okay, remember that we cannot change it. And I also least moment of inertia, we cannot change it, or the moment of inertia whichever direction the eccentric load is there that direction moment of inertia. Okay. So, now using this, one more thing important thing is that you have to understand that whatever that L by 2 root over P by EI is there, this is your what you are getting is in a radians, because this all terms are radian value. So, radians multiply by 180 by pi converts you into degrees, then only you to substitute here to get the secant value. Okay, please remember that, otherwise you will get a wrong answer. Okay. So, this is one. So, this is, if asked to find out maximum stress, you do like this. Eccentricity given to you, radius of gyration can be found out, which is I is equal to A into R square. A is known to you, and moment of inertia already found out in the direction. So, radius of gyration can be found out. Okay. So, this is what we can do. And then if it is asked provide maximum eccentricity, or what is maximum eccentricity can be provided. So, you can use a formula which is your P by A plus M by Z, right, is your allowable stress, right. So, this is allowable stress. Most of the times it is your sigma y, or with some factor of safety, that means your sigma y by factor of safety. Okay, they will give you. So, we know that P is load given to you, that we know how much load. A is known to you, M means P into E by Z we know, right. So, equal to allowable stress we know. So, from that you can find out the E. So, this is eccentricity maximally can be allowed, can be allowed if you want to put this much load P. He says that I will what I mean I am going to provide, he says I am going to provide P, I am going to provide P. So, what is the maximum E? So, use this formula and get the E. Okay. So, now there is one more, the last concept here. The last concept here is your kern of a section. As I said just now, I mentioned to you, what is that? I said P by A here, P by A plus M by Z, right. So, the question should be also there, what if, it means this is meaning basically that if this is a column, so this is one axis, this is another axis, right, assuming let us say. So, right. So, if my load is somewhere here is a P load, right. So, this becomes my eccentricity E, right. So, let us say this is a face, AA face, and this is BB face. So, for AA face what I wrote is right, the total stress, maximum stress is this, but this is for AA face of the column AA. But actually if you look at the BB face, the P by A minus M by Z is to be taken as stress, and that I said minimum stress on face BB. Okay. So, this is what is going to happen when we have a. Okay. So far I said this is maximum stress, I was working for a maximum stress. Okay. I was interested in maximum stress, worked out, but at the same time I have to be careful. At the same time I have to be careful that my minimum stress should not be less than 0. That means it cannot be 0, right. That means the P by A has to be always more than M by Z. This is my concern. That means should be always more than P E by Z, right. So Z nothing but section modulus I by Y. I is nothing but A into R square, right. So this is Y by R square with A into Y, right. So something like this. So P by A cancelled. That means E by R square, E y by R square should be always less than 1. So E should be always less than or equal to R square by Y. So that is eccentricity, right. So this is what we said, and that eccentricity I took different that distance. Suppose if I take a rectangular column, solid rectangular column, and if I try to write down a centroid like that, right. So now if the E, what I am working out, E should be less than or equal to R square by Y, R square based on the radius of gyration of the column in the direction. So this will be maybe E, and this direction will be another E, any direction, whatever direction the radius of gyration, that direction will be my eccentricity. So if you look at the points, plot the points, so I will see something like this. So this is your rhombus. That means this is the area called the kern of column, kern or core of column, beyond which if I put a load anywhere here, right, if I put load anywhere here P, there will be tension in the column, okay. Anywhere in that you will have a tension in the column, which is danger for the column. I must see that there is no tension in the column. So this we also call no tension column, no tension column. So I must see that column do not have a tension. So that area within which I can place the point load P is called kern of a column. So as a part of that, we worked out what is the distance this. Suppose this column width is your B, and this column, this side is your D dimension. So this will be your B by 6, and this distance will be your D by 6, D by 6. So this is your kern of a column we worked out, and we also worked out same concept, we derived it, and the same concept we worked out for the solid portion, solid circular. So solid circular, there will be the kern will be your circular here. So this is the maximum eccentricity E, right. Within that, any if you load place a load within this zone, then only will have a no tension, otherwise there will be a tension. So this distance we call it as capital D by 4. Okay. If the column has got, solid column has got diameter D, the kern diameter will be D by 4. You can derive again using the same formula. P by A will be always greater than your P into E by Z, that Z means A into R square by Y. With this condition, we can definitely again work out the E into Y by R square should be less than or equal to 1. From this you can work out the E. Okay. Similarly, we also worked out most of the times we use as hollow circular or hollow rectangular. So, we also worked out the hollow columns, right, hollow columns. So, within the hollow column, right, this is the center. So, right, let us say outer diameter is your d. So, then inner diameter is small d, outer diameter is capital D. So, the core or kern will be somewhere this much, right. So, this is your core, this is the core. So, this diameter of the core will be equal to capital D square plus small d square by 4. So, this will be a diameter of the core. So, you may be asked a question to find out the kern of a section, right, kern of a section, that is the area. With this diameter you can find the area or find the diameter of the hollow section. This is for the hollow circular, section, and this is for solid circular section. In fact, you can also work out, nowadays we are using hollow rectangle sections also. So, you may also work out with this using same concept. So, this is the thickness. So, assuming this is your on D and this is your B, width B, and thickness is, let us say, your T thickness, and we have the kern. So, this is your x axis, this is your y axis. Again it will be again rhombus, but exactly how much distance, that you have to work out. So, what is this dimension? So, you can work out. So, this is hollow rectangle section. Hollow rectangular section. So, this is what we can do. Okay. Again, simply we are assuming that there is no tension, there should not be tension. That means P by A minus M by Z we are using. So far we are using P by A plus M by Z because we were interested in the maximum compressive stress. We are also interested that maximum tensile stress should be less than or equal to 0. Means it is should be always positive. Okay. I mean there should not, sorry, I should say, this means this is always F greater than or equal to 0. That means P by A should be greater than always M by Z. So, this is a condition for the core, kern of a section. Okay. Thank you. I hope I gave you entire summary of what we discussed so far, and numericals you can practice, and that ends our columns and struts. In the next class we will discuss about the thin cylinder and thick cylinder concepts.